Thanks very much for the invitation. Thanks for the great talk, Whitney. So Whitney gave a great introduction in terms of structural geology, so I don't want to cover this, but I want to talk about two topics here over the next 20 minutes. One is really the thermal evolution and timing of exhumation in core complexes, and then how this pertains to hyperextended rift margins, which is sort of something I've been working on the last few years quite a bit. So what do we want to know? I mean, I think Derek already sort of asked one of the questions, and that is, what's the timing, what's the duration, what's the magnitude of displacement, what's the thermal structure of the footwall, often what's the reheating of the upper plate as you juxtaposing the upper plate against a cool upper plate against a hot lower plate. Are there structural complexities along the detachment, and so forth and so forth. So, Thermochronology does a really good job or low temperature thermochronology does a good job at doing this, and we've been doing this for like 30 years, in the brittle upper crust. So I just want to first look at the brittle part of detachment faults. And what's key ultimately is the structural integration, and as well as the accessibility to samples. And so, upper left here is a figure I made too long ago now, but that basically shows how detachment, lower normal faults, and upper crustal structures associated with them cut through the upper crust, cut through basically the different thermal sensitivity windows of thermochronometers, and exhume them by lowering a normal fault slip to the surface. And all these little dots here are essentially possible sample locations. And so this clearly shows that, in order to do this, of course, you have to have access to samples. And as Whitney just showed spectacularly in the lower Colorado River extensional corridor of California and Arizona, those are really well exposed. And you see in this picture, it's a picture I took last week. In fact, you see the Harkowar Mountains, which is a metamorphic core complex corrugation, and you see the Harcohalis down here. It's another metamorphic core complex where the upper plate is basically pulled off to the northeast, and you get these 50-kilometer long footwall corrugations that really allow sampling. Core complexes, however, come in all kinds of shapes and forms. They come in different metamorphic terrains. They come in different rocks. And so I've been quite fortunate to sort of look at other examples around the world. Here are some of my more favorite examples in the Cyclades. In terms of structural context, it always helps if you actually have, your graduate students act out, kinematic indicators. So you have a structural context. So in this case, the footwall is made out of blue schists, and or at least retrograded blue schists. Fantastic exposures. Too much ocean compared to the western U.S., so you get a little bit less continuous exposure. And then you have on the right-hand side here, somewhere where I was doing work a few years ago now, is in Damon Dome in Papua New Guinea, which is sort of a classic example, or one of the examples of an active metamorphic core complex. Beautiful place, but really hard to sample. It's in the jungle. You basically have a basaltic footwall in this case, which doesn't lend itself very nicely to thermochronology necessarily either. So there are basically two sort of large scale approaches here in terms of thermochronology, and I'm going to talk about petrochronology a little bit later. You can either throw the kitchen sink at it, which is the upper right-hand corner from a metamorphic core complex in Baja California, where you basically have a single sample, or you have multiple samples, but you basically try to do just about everything you can do, from uranium lead to argon to uranium thorium helium to fission track dating. And so you're basically trying to reconstruct the entire thermal history with multiple thermochronometers on a single sample. The other possibility is that you're actually having a transect or a spatial array that's structurally controlled of either a single thermochronometer or multiple thermochronometers. And in addition to that, we have sort of learned, a lot about new thermochronometers over the last, couple of decades, mainly in the uranium lead space and the uranium thorium helium space, that allows us to not just look at granitic footwalls, but more complicated metamorphic or even mafic to ultramafic footwalls. So here's just sort of an example of what we sort of generally tend to learn from low temperature thermochronometry with respect to the unroofing of metamorphic core complexes along the normal faults. Here's another example of probably an active loinal normal fault system in central Tibet. And what you see here is basically the footwall. You have growth strata in the upper plate, and you can see that in blue here the apatites, and in these orange diamonds the zircon, uranium, thorium, helium H's. How they sort of get progressively younger in slip direction. And so you can clearly see that this is a Pliocene to Pleistocene rapid unroofing of this metamorphic core complex. However, in the detrital section of this growth strata, you see lots of Miocene ages preserved, so you get the detrital record, the detrital thermochronometric record of the earlier part of this. And so often, if you just have access to the footwall, you really potentially only get at the latest part of the exhumation history. Here's this example from Damon Dome in southeastern Papua New Guinea. You see this beautifully exhumed Pliocene dome that's corrugated. You have a loinal normal fault. In this case, the footwall is mostly made out of basalts and gabbros. And so what you see down here are zircon, uranium, thorium, helium H's that go from 0 to about 4 million years. Again, you can see that they get from left to right older as you go up dip along the lower normal fault. Okay, good. So let's get to the Whipples here. There's a classic view that Whitney already showed. And so, many years ago now, we did this transect basically for about 50 kilometers, or not quite, maybe 40 kilometers from the up dip end of the footwall through the myelinitic front into the footwall myelinites of the Whipple metamorphic core complex to the down dip end of the exposure in slip, more or less in slip direction. And what you see, even though I've flipped it here, is that for apatite helium, you basically go from about 23 million year olds or 22 million year old samples here, continuously down, and you step back up. You do the same thing for the zircon helium H's essentially. And you see at the up dip end here, more partially reset samples. So you're above the partial retention zone. So you're below temperatures pre-extension of probably about 140 degrees Celsius. Okay. So clearly you learned something about the timing, in this case, of the onset of brittle faulting along the detachment fault. I mean, we can talk about the ductile part here some other time. The other thing you learn is that when you go to the down dip end, you actually start to see these repetitions in the thermochronometric data that tells you that there's probably subparallel, normal faults that kind of sliver and in size some of the footwall and transferred sequentially to the hanging wall. So we can also learn something about the structural complication along this the loinal normal fault. That might be otherwise, hard to see. One thing people really like to do is, like, once you're below the partial retention, or once you're in a totally reset zone, and we've seen this, you have H's that are basically getting younger in slip direction, and people like to actually use that to leverage slip rates. But that's fine, but there's a whole bunch of assumptions that are basically going into these calculations or these estimations. One is that you have a steady state, thermal structure. You have a coherent footwall that's not extending by itself, that you have a constant fault dip angle. And probably the most important one, and often probably the most violated one, is that you have that all the vertical exhumation is related to footwall exhumation along this lower normal fault, which essentially precludes upper crustal or upper plate extension. So you cannot thin the upper plate, because that would have an additional vertical advection component. Okay, but fine. So we've basically seen, and a lot of people have seen, so anywhere from like 2 to 7 kilometers per million years of slip rate along these lower normal faults, which is certainly substantial. Now, more recently, with Rich Ketchum, we've done thermokinematic modeling in 2D. Which sort of, is probably a better way than to just regress a line. And so there's this paper by Lutz and others from last year that actually did a very nice job at looking at the progressive evolution of the footwall geometry and its influence on the thermal structure and therefore the cooling history in the funeral mountains of the Death Valley region. But what I really want to talk about here in the rest of my talk is the temporal and thermal evolution of hyperextended rift margins. So what you've seen so far is essentially pretty simple cooling. You're pulling the footwall up along a normal fault, and things cool or overall pretty well behaved, unless you have some complications along the normal fault. And so here's just a little motivational slide from my class last Friday. We did some sandboxments, and so if you have sediments, that's of course very useful in terms of giving you insights into the timing and thermal structure in terms of thermal maturation indicators. But often you don't have that, or the rocks are simply not accessible. One of the things I think that's really sort of, wouldn't say set us back, which has been really useful, is the sort of Mackenzie pure shear model that kind of made a lot of predictions about subsidence and tectonic. Yes, tectonic.
You used 12 minutes now. Sorry
Good.
for continuing.
Thank you. About tectonic subsidence and thermal subsidence. And while this works really great, once you get to large beta values, generally tends to break down, and you're certainly not predicting the thermal maturity indicators very well. And so we need to do better, basically. And so one of the things we have been doing is sort of looking at progressive rifting in the distal and proximal margins of hyperextended margins as you go from basically the initial rift phase through the hyperextension and thinning phase to mantle exhumation. So that's what I want to talk about here for the remaining minutes. So with the student, Nicole Hart, we looked at the thermal evolution of the proximal margin in the hyperextended system in the Western Pyrenees, the Molion Basin. And basically here you see these orange faults are the faults of the proximal margin, and in red here is a normal fault, the North Molion detachment that eventually leads to probably mantle exhumation. So one of the things we've seen when we did these one of the things we saw when we did this work is that we actually we get very high geothermal gradients. You do vertical transects within these rift blocks that are easily reconstructable because you have to preserve iastic unconformity. And one of the things we've seen is basically that your geothermal gradient is often 90 to 100 degrees Celsius per kilometer. Incredibly hot, and that's something that's supported by the thermal maturation of the center of sediments. So how is this? Well, we did some modeling with Luc Lavier, and others have done this too. And one of the things we've seen is that like depth-dependent thinning, especially under the H block, tends to heat up the crust during hyperextension pretty dramatically. And you have, as you can see here in this model, say the 200 degrees C isotherm climb up into the basin and really heat the thinned upper crust quite dramatically. So we have in the upper crust lots of evidence now that you have during depth dependent thinning during the early parts or during necking, you actually have very high geothermal gradients. Well, why is the crust not melting? Well, the crust is probably not melting because it's already thin, and that's sort of supported by the presence of plagiogranites in the sublithospheric mantle right below it. But do we see this reheating in the lower crust? So in order to do that, what we want to do is actually briefly look at the high temperature thermochronometers, both apatite uranium lead, rutile, and zircon uranium lead in terms of metamorphic rims. So a few years ago, my then graduate student, Nikki Seymour, and I went to Corsica and looked at this fossil hyperextended rift margin that's exposed. And it's been long known in Corsica that you actually have this reheating that leads to these resorbed garnets with these stranded concentration profiles, and they've always been interpreted as being Variscan. But once we started analyzing the zircons around these garnets, what we started to see is that you have metamorphic rim overgrowth that are consistent with garnet breakdown that are in fact Jurassic in age. And so this heating in the lower crust in Corsica and the and the breakdown or resorption of these garnets is clearly related to heating of the lower crust during Jurassic rifting. So what we see is that basically zircon and garnet records Jurassic reheating, whereas then the rutiles and apatites, basically are younger and record the post-reheating exhumation and breakup along the margin. Apatites, though, are quite interesting in that they actually are more than just a chronometer. They're also a really good geochemical recorder. And what we see here, this is from a case from the Pyrenees, is that if you get magmatic zoning, you basically get your old Variscan ages, you get probably ductilely deformed apatites that give the rift age. And then we also see these really sort of mottled apatites here that are probably recrystallized in the presence of fluids. When we look at those, we actually see a really interesting trend. And that is that the old domains basically record the Variscan original magmatic ages, but the trace elements that are most indicative of fluid flow are reset. And they're, in fact, the chemistry tells you that it's an ultramafic fluid. And so this is sort of what we basically envisioned, is that you actually get during serpentization, during the early parts of mantle exhumation and high temperature metamorphism that's recorded in the sediments above those mantle rocks, you actually get fluids that go along the long normal fault and actually recrystallize or help recrystallize some of those apatites. Good. So what about the distal margin? I want to finish up here in the last couple of minutes looking at the distal margin, which often, unfortunately, we don't have access to because it's covered by the passive continental margin or it's far offshore and it's probably never going to get drilled. So one of the few places where we actually have access to the distal lower plate margin is on Zabregod Island in the middle of the Red Sea. So this is a reconstruction at the onset of rifting in about 23 million years, but Zabregod Island is a really interesting place because you have a super thin lower crust that's juxtaposed against sublithospheric mantle along the long normal faults, maybe modified by mantle diapirs. You have a pre-rift sedimentary section right on top. So you really have a crustal section here that's just a couple of kilometers at max thick, and it looks very much like that the Tosna section that John Reto or Ottmar Müntener have published on, and many of you might have seen. So interestingly enough, here the zircons basically tell you it's lower Neoproterozoic crust. That's interesting. But we do find actually, or other people have, in this case, Bosch and Prigier have documented a while ago that there are actually syn rift zircon rims. Again, that's probably related to reheating. If you look at the apatites and rutiles, however, they're really young. They're basically, latest Miocene to early Pliocene in age. And so what we basically see is that you have maybe a little bit earlier reheating, you have largely cooling, but you have this reheating event almost temporally coincident with oceanization or seafloor spreading in the southern Red Sea. So how is this? So what we envision here is that basically as the seafloor spreading propagates northward from the southern Red Sea towards Zabregod Island, is that the distal margin, which is preserved on Zabregod Island, essentially gets heated from below, and the thermochronometers, because the crust is so thick, the crust, or in this case, the pre-extensional lithosphere, is so thin by now that you're basically getting exposed from below to the encroaching magma chambers related to seafloor spreading. This is a model that actually was originally put forth by Marco Ligi in 2012, but that's sort of, this is sort of really the data that show that there's a tremendous thermal impact on this. So what I want to leave you with here is that, metamorphic core complexes, fabulous things. Cooling histories are often, which is nice, relatively simple. But when you go to hyperextended margins, basically the mantle starts to play a much greater role in terms of the thermal budgets, both during depth-dependent thinning, during mantle fertilization, serpentinization during the hyperextension, as well as oceanization from below in the distal margins during final breakup. So the mantle certainly makes it more complicated, but it's something that we can shed light on using both low and high temperature thermochronometry and thermal processes that are important in terms of understanding the rheology of the final lithospheric breakup. Thank you very much.
Awesome. Thank you very much, Danny. I'm going to open the floor to questions now. I have one. Perhaps we can start with that. So I am wondering, and you've probably answered this question during your talk, but I probably missed it. These models assume pure deep sleep exhumation throughout the life of the detachment fault. If at some point during extension we have stress rotation and you have, exhumation in a more oblique kinematic pattern, is there any way to track that?
I think it's a good question. I think, in places like the Whipples or the southwestern U.S., where the detachment faults are highly corrugated, it's probably pretty difficult to sort of move against the corrugations. And so even if you have this maybe a stress rotation, I mean, it's like taking two corrugated irons and trying to slide them in a different direction. That's probably hard to do. But what we have seen in the Whipple Mountains is like late stage, when you sort of maybe have deformation associated with San Andreas faulting, you do get brittle strike slip faulting that cuts across. And we've done a lot of calcite uranium lead dating over the last couple of years on strike slip faults in the southwestern US that sort of dates those faults, and they're mostly sort of 9 to 3 million years. So we know when the systems essentially die, but I think actually having them slip into different directions mechanically pretty difficult.
I have one. I don't know if it's going to expose my ignorance. In terms of the Red Sea, this idea that the thermochronometers for the shallow stuff get adversely affected by the mantle effects as we get nearer to seafloor spreading. How easy is it to separate those out in a margin you maybe don't have a lot of information on? Like, how do you unpack the two and separate out the influences, or can you?
Yeah, I think that's a good question. I didn't use the word adversely, but I mean, unfortunately, we don't have access to distal margins very often. So as I said, in terms of nobody wants to drill that deep. It's often covered by lots of sediment, super deep water. And so we have a few places where either in the Alps or in the case of Sabregat Island. So I think what actually helps very often is the sediment cover. Like in Sabregat Islands, these are Cretaceous pre-rift sediments, but you hit them with a hammer, they're essentially glass. So there's a lot of basically silicification that goes with it. So there's a lot of fluid flow. And so the thermal maturation of the sediment that sits directly on top of those thin distal margins usually is really cooked. So that might actually help you. And so, people have done fluid inclusion work in some of those sediments. People have done Raman spectroscopy. I think in the Pyrenees, for example, you see that a lot of the sediments that sit directly on the mantle, even though that's probably not related to ozonization, but mantle exhumation, are really, I wouldn't say hyper mature, but certainly much more mature than they should be, judging from Raman spectroscopy.
Cool, thank you. That makes a lot of sense. There's a question in the chat.
I'm struggling with my chat now. Kim, can you?
I can read it out. It's
right,
fantastic tool de force across metamorphic core complexes around the world. Thanks for sharing. Can you comment on the link between active metamorphic core complexes and geothermal energy? Sorry, no audio here.
Sure, I can try. I mean, I've done a fair amount of work in geothermal resources in Nevada using thermochronology and thermochronometry, and sort of certainly can be a very useful tool to sort of delineate long-term high temperature fluid flow. But I, I'm not sure how much, at least in the Western U.S., most geothermal resources are not related to long normal faults. They're often related to, you know, to fault steps in in sort of high normal faults, because you have to constantly rejuvenate your fracture permeability. And so, so I'm not sure how well low normal faults lend themselves to actually, do that. But I'm sure, yeah, I don't want to kill off anybody's low angle normal fault geothermal project here. So.